Hello everyone, my name is Krishna Murari, and in this video I will be discussing about computational results and its interpretation obtained for my project using two softwares, ORCA and Crystal Explorer. The first task that was assigned to me was that I have to perform geometry optimization with opt plus frequency for ethylene glycol and acetone. This one slide is showing the results for ethylene glycol. I have done the geometry optimization for both ethylene glycol and acetone, and these are the results. This one is for ethylene glycol, and this one is for acetone. The structure that is showing here, the structure which is showing here is the optimized structure of ethylene glycol. For confirming the convergence of the optimized structure of ethylene glycol and acetone, you have to check the output file that you have obtained from ORCA. Search for the section near the end of the file that reports convergence. There you will see the convergence check. If it is okay, then it is fine. The method that I have used for geometry optimization is DFT, and the functional that was used was B3lib, and the basis sets that were used were 631G DP Gaussian function and with polarization D and F function. The optimized structure is shown here. Its optimized energy is minus 21.09 kilocalorie per mole. Also key distances, these are the bond lengths, key bond lengths, and these are the key bond angles, and these are the key dihedral angles. All these data have been computed using Avogadro. Also, the dipole moment for the molecule was calculated, which was coming out to be 2.41 dBi. Now these are the results for acetone. These are the key bond lengths, these are the key dihedral angles, and these are the key bond angles. And its optimized energy is minus 21.36 kilocalorie per mole. Its dipole moment was also calculated. That was coming out to be 2.82 dBi. Here you can see. Now we have generated IR spectrum for glycine, and now for generating IR spectrum using ORCA, you have to first optimize the geometry of glycine to obtain its lowest energy structure. Then you have to perform the frequency calculation. This calculation provides the vibrational frequency and IR intensity. Now using this data, you can plot IR spectrum of glycine. This is the theoretical IR spectrum of glycine that I have generated, and this one, the above one, is the experimental IR spectrum. If you just focus on the peaks, not on the intensity of the peaks, you will find that both these IR spectrums are more or less similar. Now, I have performed geometry optimization for cis 1,2-dichloroethylene and trans 1,2-dichloroethylene and computed its ground state energy. Ground state energy for cis isomer was coming out to be minus 997.77335 Hartree, and for trans isomer it was coming out to be minus 997.77311 Hartree. Now from computational result, you can clearly see cis isomer is more stable than trans isomer, but this is not experimentally true. Trans isomer is more stable than cis isomer because of mainly two reasons. First is in case of cis isomer, you have two big chlorine atoms that are present on the same side of the ring, and chlorine have lone pair of electrons. They will cause repulsion, due to which cis isomer is less stable. And second one is the dipole moment. In case of trans isomer, dipole moment is coming out to be zero, and lower the dipole moment means lower energy and greater stability. So sometimes even computational results may be misleading. Here. Example for here, computational results are saying cis isomer is more stable than trans isomer, but experimentally it is proven that trans isomer is more stable as compared to that of cis isomer. Now these are the HOMO and LUMO diagrams of butadiene. Highest occupied molecular orbital, and LUMO is lowest unoccupied molecular orbital. For obtaining the orbital diagram for HOMO and LUMO of butadiene, we have to first optimize the geometry of butadiene, and after that we have to generate more molecular orbitals. Then you will get the output files corresponding to HOMO and LUMO, which can be visualized using IVO view software. And And in this last slide of ORCA part, I have generated electrostatic potential map for ethanol and dimethyl sulfoxide. In electrostatic potential map, red region indicates electronegative part, whereas blue region indicates electropositive part. And these are the partial charges for each atom that have been computed. This one is for ethanol and this one is for dimethyl sulfoxide. In ethanol, you can clearly see the partial charge on oxygen is coming out to be minus 0.5368, which is indicating that oxygen is the most electronegative atom present in this ethanol molecule, which can be clearly visualized using the electrostatic potential map. Here, oxygen is clearly clearly in the region of red one, which is clearly indicating it's more electronegative. Now, if you will see dimethyl sulfoxide, if you will see partial charges on oxygen atom, it is coming out to be minus 0.6267. It is the most negative of all the partial charges that are given here. So, from partial charge data, we can clearly say oxygen is the most electronegative, and this can be visualized using electrostatic potential map, which is also indicating that this one is the more electronegative part. Now, moving on to the lattice energy calculation part. Now, in this part, I will tell how to calculate lattice energy using Crystal Explorer software. Before we move ahead, we should know what is lattice energy. Lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into its constituent ion in the gaseous phase. In the Crystal Explorer, we cannot directly calculate lattice energy. We calculate lattice energy using some approximation. In Crystal Explorer, lattice energy is calculated by summing up all the pairwise interaction energies for a single molecule in the crystal lattice. Let us discuss the computational method by which we calculate lattice energy using Crystal Explorer software. Before lattice energy calculation, we should know how to calculate nearest neighbor cell interaction energy. Here it is written. First, the nearest neighbor cell interaction energy values were calculated by summing the pairwise interaction energies for all the molecules within the range of 3.8 angstrom distance from the molecule in the asymmetric unit. First, what we do, we first generate atoms within the cluster radius of 3.8 angstrom from the central molecule. Then we calculate pairwise interaction energy, and then we sum it up, and after that we calculate nearest neighbor cell interaction energy. Right. In the same way, here it is also written. In the same way, lattice energies are estimated by the same method, but the molecular cluster was extended until the sum converged. Here is a screenshot. It is from Crystal Explorer website. It is clearly showing that for non-dipolar molecules, a radius of 20 angstrom should be sufficient, and for more dipolar molecules like amino acids, bitter ions, which contains longer long range interactions, they require a cluster radius of 30 angstrom or more, right? But in most of the cases, we will get a convergence of interaction energy sum for a cluster radius of 15 angstrom. So you don't need to go beyond that. And even in my calculation, I have used 15 angstrom. Now, let's start with how we have calculated nearest neighbor cell interaction energy. Then we will move further to the lattice energy part, and then we will discuss the results. Uh, Now, how we will calculate nearest neighbor cell interaction energy? First, we have to generate atoms within 3.8 angstrom of the molecule in the asymmetric unit, and then we calculate interaction energy using B3 lip 631G. Here it is written accurate. We are using accurate one. It will, of course, it will take time, but it will give accurate results. Uh, then we calculate interaction energy using this one, and after that, you will obtain a chart. This one is this type of chart you will obtain. It will show on the screen. Then what we have to do? We have to just export this data to an Excel file, and after that we calculate nearest neighbor cell interaction energy by multiplying column n, this one column n and E total, and then summing up the values and then dividing by 2. Now, why we are dividing by 2? Let me tell you once more how to calculate. We just multiply this column, n column, into E total, and then sum that up, and after that we divide it by 2. Why we are dividing by 2? Because we calculate nearest neighbor cell interaction energy in kilojoule per mole, and here we are calculating intermolecular energies that is between two molecules, so it is over counted. So to reduce that over counting, we are dividing it by 2. Now, for we have I have calculated nearest neighbor cell interaction energy for three molecules, that is fluorouracil 0 2 polymorphs of fluorouracil, and one pyrene structure. For fluorouracil, the nearest neighbor cell interaction energy was coming out to be minus 76.8 kilojoule per mole. Now, we have done the lattice energy calculation. For lattice energy, we have to generate atoms within 15 angstrom cluster radius and repeat the same procedure. You will get first generate atoms within the 15 angstrom of the uh, 15, 15 angstrom cluster radius of the molecule. You will obtain a file like this. You will obtain a chart like this. You have to export this chart into Excel file. Then you have to multiply this n into E total, and then after you have to sum of all the interaction energy, then divide it by 2, you will get the lattice energy. All the calculation that I have shown here is for fluorouracil. Its lattice energy is coming out to be minus 121.75 kilojoule per mole. Now, here is a screenshot which is from Crystal Explorer software website, which clearly tells us how to calculate lattice energy. Here it is written, lattice energy can be sorry. Here it is written, lattice energy can be obtained as one half of the product of two columns labeled n and e total, where n is the number of molecule pairs in the cluster with that particular interaction energy. In the same manner, the lattice energy can be broken down into separate contribution, electrostatic dispersion, node. Sorry. Now, what in this assignment that we have done, we have to check the stability of two polymorphs of fluorouracil. We have calculated lattice energy of both the polymorphs of fluorouracil using the above method, lattice energy estimation method, and found lattice energy for fluorouracil to be minus 121.75 kilojoule per mole, and for fluorouracil 0.2, it is coming out to be minus 135.2 kilojoule per mole. From this data, we can clearly say fluorouracil 02 polymorph is more stable, as thermodynamically more stable as compared to that of fluorouracil 01 molecule. Similarly, lattice energy for pyrene is also calculated, which is coming out to be minus 106.8 kilojoule per mole, and we have calculated it to cluster radius of 20 angstrom. And now, these are the contribution of various factors that are present there. It is Contribution of various factors are given here. First one is electrostatic part, which is contributing minus 23.5711 kilojoule per mole. After that, polarization energy is there, which is contributing minus 3.996 kilojoule per mole. Then after, dispersion energy is there, which is minus 145.283 kilojoule per mole. And last, its repulsive energy, whose contribution is 66.9912 kilojoule per mole. Sim Similarly, pi-pi interaction, which is nothing but dispersion energy contribution to the lattice energy, this can also be calculated using the same method. Just we have calculated the lattice energy part. Its percentage contribution is coming out to be 136.032%, which means it has positive contribution in stabilizing the crystal structure of pyrene. See, here there are four types of different interactions: electrostatic, polarization, dispersion, and repulsion. Electrostatic, uh, polarization, and dispersion, they are positively contributing to the overall stability, whereas repulsive forces, they are negatively contributing. Positively means they are stabilizing the crystal structure of pyrene, and repulsive forces, they are destabilizing the crystal structure of pyrene. And in the last part, we have compared the pi stacking energy with the hydrogen bonding of the hydrogen bonding interaction with the 5 fluorosyl uracil structure. Dispersion energy in pyrene is coming out to be minus 145.283 kilojoule per mole. Hydrogen bonding interaction is coming out to be in case of fluorouracil 01 minus 91.69 kilojoule per mole, and in case of fluorouracil 02, it is coming out to be minus 113.522 kilojoule per mole. From these data, we can clearly say dispersion and interaction energy in pyrene is coming out to be is mainly contributing from pi stacking interaction. Pyrene is nothing but this type of ring. Aromatic rings attached to each other. They would have electron clouds above and below the planar aromatic ring. They were attracted by the pi stacking interaction, and this dispersion energy is we can clearly say this dispersion energy is mainly contributed from pi stacking interaction. Now, electrostatic interaction from these hydrogen bonding interactions, which are nothing but electrostatic interactions, we can say that electrostatic main contribution in electrostatic interactions in coming from hydrogen bonding interaction. Now, this is all that I have. Thank you for the now. Thank you.